Welcome back, students. Now that we have thoroughly investigated diatomic molecules, we're going to turn our attention to polyatomic molecules. MO theory is applicable to polyatomic molecules, but it becomes much more challenging to combine atomic orbitals when you have 3 or more atoms involved in the molecule. Today, our focus is going to be on constructing hybrid MOs. And this is the way in which we can go about connecting our molecular orbital theory to our more conventional understanding of how bonds work. So the learning goals for today are going to be to compare and contrast our valence bond theory, which is going to be the underlying theory behind hybridization. We're familiar with hybridization, and our more modern, maybe our more based in quantum mechanics molecular orbital theory. And I've mentioned already in class and maybe in the lectures as well a few times about the contradictions between these. So we'll see this come to a head in the next lecture, but we'll begin to discuss some of these ideas today as well. At this point in our chemistry careers, we are pretty comfortable determining the shape of a molecule. If we have some molecule like ethanol, we are very comfortable describing the ways in which the molecules will arrange themselves in the bonds. And this, in general, we may not remember this, or maybe we do for Gen Chem, is called the VSEPR theory. So it's the valence shell electron pair repulsion model or theory. And we're, of course, very comfortable with this. We have things like trigonoplanar, trigonal pyramidal, tetrahedral bent, the more complicated structures down here. And we're pretty good at describing this. There's even rules that we can use that you probably didn't go into too much in Gen Chem that determine the relative bond angles for things. So like lone, and this is the one you remember is that lone pairs take up more space than an atom, but there's also things about double bonds taking up less space and so forth. The problem that we're going to have here is that this model very much implies that our electrons are in lone pairs or bonds. And we just saw with MO theory that our electrons are spread out over the whole molecule. So we want to try to reconcile these models. So this VSEPR model is a localized model where electrons are localized in bonds and lone pairs, while MO theory is a delocalized model where all electrons are delocalized over the whole bond and really essentially over the whole molecule. The kind of ideas that we have to wrestle with here are, is one of these ideas right? Is one of our models wrong? We've used them both basically throughout all of chemistry. And it turns out that they're both conceptually useful. So MO theory is useful because it's based in quantum mechanics, and VSEPR theory is useful because it is more intuitive and it allows us to easily predict shapes of polyatomic molecules. And MO theory, on the other hand, allows us to easily predict the energies of electrons and orbitals using quantum mechanics. So we're going to be highlighting these discrepancies between these two models, and eventually in the next lecture, we are going to attempt to reconcile them. So keep these ideas in the back of your mind as we go through the sections of this chapter. The connection between these two models has its root in hybridization theory, otherwise known as valence bond theory. And you will be familiar with this from organic chemistry. This is the idea that electrons are in hybridized orbitals or hybrid orbitals. And again, this is a localized bonding model. We still have this localization that we'll deal with next time. And so what's going on here is that what we're trying to do is mix together atomic orbitals. And so you're familiar with the kinds of hybridization that carbon have. We have sp, sp2, sp3. And essentially what these designations mean is that what we're doing, so say when we're taking an sp hybrid orbital, is we are going to mix together an s and a p orbital in some way. Now, just like when we did this with MO theory, when we mixed, say, 2 hydrogen 1s atom orbitals together and got a bonding orbital and an antibonding orbital, if we mix an s and a p orbital together, in this case, they're both coming from carbon. So this is a little bit different than MO theory in that our orbitals are being hybridized of the same atom. We're still going to get one orbital for each orbital we put in. So if we put 2 atomic orbitals in, say sp hybridization, we get 2 sp hybrid orbitals out. And the same is going to be true for sp2 or sp3. So essentially what we're doing here is taking linear combinations of s and p orbitals, adding them together, and getting new hybrid orbitals. And you'll be familiar with this from organic chemistry. These orbitals are going to point in the different directions. So for example, if we're going to look through sp2 hybrid orbitals and actually construct hybrid orbitals here for sp2 hybridization. We know that what we're doing here is we're mixing together 1 s orbital and 2 p orbitals, and they should be pointing in these 3 different directions in accord with having a trigonal planar geometry, so the bond angle here should be 120 degrees. What we can do is actually, at this point, we can do the math. We have enough math developed in this class that we can actually add in together s and p orbitals and come up with the sp3 hybrid orbitals. So let's go ahead and look into this. All right, so here we are with our hybrid orbitals, and what we want to do is try to build these out of s and p orbitals. We're arbitrarily going to choose here the p or the pz and the px orbitals is what we're adding together, and leave out the py orbital, but you could do this with any dimension. So what we're going to do is we're going to construct 3 hybrid orbitals. We're going to have a psi A, psi B, and psi C. And we're simply going to add together S and P character. So we'll go ahead and say that psi A is equal to C1. So this is just, the C's here are going to be normalization constants. So it's equal to C1 times 2pz, so some contribution from the 2pz orbital, plus C2 times the 2s orbital, plus C3 times the 2px orbital. And we're going to do this for all 3 of our orbitals here. The next thing to do is going to be to use some arguments from geometry as to what these coefficients should be. So the first thing we're going to note is that our s orbital is spherical and will therefore have to contribute equally to each hybrid orbital. So what that means is that our coefficients for 2, 5, and 8 here, the ones that determine the s character of each of these orbitals, are going to be the same. Now, what are they? Well, what we're doing is we're splitting up our s orbital into 3 hybrid orbitals. And what we have to remember is that our orbitals need to be normalized. So that means that the sum of these, and specifically it's the sum of the square of the magnitude of these coefficients, must equal 1. And that will account for all of our s character. So if this is the case, we will determine that these coefficients are equal to plus or minus 1 over the square root of 3. And we are actually going to choose minus 1 over the square root of 3. Why minus? Because the s orbital we're talking about here is the 2s orbital, and that starts at positive and then crosses a node and becomes negative. So to ensure that that orbital is positive in the regions where it would be overlapping with p orbitals, we choose a negative sign, so it starts negative and then goes positive when it crosses its node there. So now we've solved for all the s orbital contributions, but what about the p orbital contributions? We'll start with psi A there, and we'll note that psi A up here is wholly in the z dimension. And what that means is that C3 is going to end up equaling 0. There's no x contribution for the psi A orbital. What we'll also note is that the x contribution for the B and C orbitals are equal and opposite. So the C orbital goes in the positive direction and the B orbital goes in the negative direction. So we'll get negative C6 is equal to C9. We can make a similar argument and say, well, both of these go down to an equal degree. So that means that C4 is equal to C7. And here we have a simplified version of what this should be. Plugging in all of these coefficients gives us the following set of equations which we want to solve. how we're going to do that is essentially by taking a couple of steps, orthogonalizing and normalizing these various functions. So we'll start with psi a there, and we'll note that those coefficients, so our C1, C2, and C3, have to add up to 1. This is just like when we were making wave functions before out of sums of various other wave functions. The total wave function density has to equal 1. The wave function has to be normalized. So what we're going to do is ensure that our psi a is normalized. And of course, we do that by taking the integral of psi a star times psi a and integrating over its various spatial coordinates and setting that equal to 1. So what does that get us here? Well, it gets us 4 functions, but remember these 2pz and 2s orbitals are all eigenfunctions of the same total energy operator. And what that means is that anytime we multiply 2pz times itself, that's already normalized, and that integral is going to be 1. And the other integral, if we had 2pz times 2s, that is equal to 0. So if we were to go carry this whole integral out, and I'll do it here just for this one, we would end up with 2 integrals. So we would get 2 times c1 over the square root of 3, and this should be negative. And that will be the integral of 2pz, 2s. And then we'll have a plus c1 squared times the integral of 2pz squared. And then we'll have plus 1 over 3 times the integral of 2s squared. Since these are orthogonal already, these wave functions themselves, this integral is 1, this integral is 1, and this integral is 0. And what we end up with then is 1 equals c1 squared plus 1/3. So we can go ahead and evaluate this and determine that c1 is equal to the square root of 2 over 3 if we were to solve this equation here. Now, the next step is going to be to use this to solve for another one of our variables. So what we're going to do is we're going to ensure that these hybrid orbitals are still orthogonal. So we're going to say that the integral of psi a star times psi b must equal 0 to be orthogonal. So if we do this, again, the only terms that are going to appear are the ones where we have the same function multiplied by itself. So what that gives us then is we're multiply this function psi a times psi b, and we're only caring about the terms that have the same wave function. So this gives us c4 times the square root of 2/3, and then we're going to have plus 1/3, and then that's all that we're going to have there. Because the other one has no 2px component. So here we can get that negative 1/3 is equal to c4 times the square root of 2/3. We want to multiply that by the square root of 3/2 on each side. And so the square root of 3/2 times negative 1/3 is equal to negative 1 over the square root of 6, and that is equal to c4. Finally, we need to solve for the last thing here, which is c6 and c9. And to do that, we just have to ensure that psi b is normalized. So we'll do the same thing. 1 has to be equal to the integral of psi b star times psi b. And what that is simply ends up being 1/6 plus 1/3 plus c6 squared. And so c6 is equal to 1 over the square root of 2. So we can put all of these things together and get an equation for these hybrid orbitals. And I'm going to bring you back to the slides to show that. So here we get these equations with all of the constants put in. And if we were careful and wanted to attempt to plot these things, we would find that these hybrid orbitals are represented by this linear combination of the atomic orbitals. Note that each hybrid orbital, if we were to square and sum the magnitudes of these normalization constants, we would get 1. And also each normalization constant is evenly split up. So there's in all three of these hybrid orbitals, we have 100% of the pz orbital accounted for. 2/3 of it is in this orbital, and then the other 1/6, or the other 1/3 is split up evenly between these two orbitals, and so forth. So none of our orbitals have gone anywhere. We simply rearranged where the orbitals are. If we wanted to, and we'll probably go through this in class, we could evaluate these and show that they have their positive densities pointed at 0, 120, and 240 degrees, like we expect them to. We can also construct hybrid orbitals for sp3 and sp2 hybridized carbons, noting that the larger p character we get in a hybrid orbital, the smaller the bond angle is. So sp is mostly s character, it's 180 degree bond angle. sp3 is mostly p character, and that has a 109.4 degree bond angle. It's much smaller. I'll briefly mention Bent's rules here. So Bent's rules, and you know Bent's rules, although not under the name, they're essentially that our hybridization rules. The number of atoms in lone pairs determines the hybridization. But what we don't really get in the way we normally learn this in organic chemistry is that you can have different hybridization assigned to different ligands. So if you have inequivalent ligands, for example, a hydrogen atom in a lone pair, as you would in the water molecule, you actually have a different kind of character. And that makes sense if we go back a slide here and think about this. What's the bond angle of water? Well, it's smaller than 109.4. It's 104.5. And so what that actually means is that our water molecules have less S character. They have more P character than an sp3 hybridized carbon. How much character do they have? Well, we can look into that. So naively, we would predict, using those first set of Bent's rules, that water is sp3 hybridized. But if we actually describe the hybrid orbitals, we find that that's not the case. So I'll mention here that our hybridization model is not capable of predicting the bond angle. There's no reason why water would have a bond angle of 104.5. But if we go into the hybridization model knowing that water has a bond angle of 104.5, we can construct hybrid orbitals for it. So how do we do that? Well, essentially, we just bring up this sort of model here, where our hybrid orbital for water is the sum of, again, px, pz, and 2s. And this is related. So there's a relationship between the constants here. So cosine theta and sine theta determine the bond angle, right, as you increase theta. So if theta was 0, cosine of 0 is 1, and sine of 0 is 0. So these bond angles would be 100% in the z dimension. And the same is true if theta is 180. And then we just have some contribution from the 2s orbital in terms of this alpha here. So what we want to do is ensure that these orbitals are still orthogonal. So just like we saw before, we'll orthogonalize these orbitals. So if we multiply them together, they should equal 0. And what that gives us then is that we have this term in brackets here, again, just actually solving the integral. We end up with cosine 2 theta plus alpha squared is equal to 0. And that means there's a relationship between alpha, which determines how much S character the orbitals have, and this theta, which actually is reflective of the bond angle. So if we change the bond angle, we have to change what alpha is. So we can come in here and change this. We can plug in that 2 theta is equal to 104.5, or that theta is equal to 52.25. We can come up with this expression simply by, again, evaluating what these things are. And then we can also normalize, we'll go through this in class, take the normalization constant. And what we find is that this molecule is sp4 hybridized, this oxygen atom. Now, how do we come up with that? How can we mix 4 p orbitals in there? Well, what we've done is simply square the magnitude of each of these coefficients. So if we square the magnitude of 0.54 plus 0.71, and we square those and add them together, we get 0.8. And if we square 0.45, we get 0.2. And so that means that this hybrid orbital here, and it's the same for the B hybrid orbital, is 20% S and 80% p. So there's 4 times as much p as there is s, hence it's an sp4 hybrid orbital. We can also construct orbitals for the lone pairs with the remaining contributions that haven't been accounted for here, and we'll go over that in a homework problem. And it's not as nice and neat as sp4 in terms of the answer we get. So with this, we can see these orbitals, we can visualize them, and they look kind of like we expect here. Next time, we're going to look into more detail at this model and try to, again, actually decide where the electrons are. They can't simply be in these localized orbitals. It doesn't make sense with our molecular orbital theory. So we're going to bring these two models head to head and see what we can say about each of them. And so I'll stop there. We'll go over this again in class to look through the math in a little bit more detail. And I will see you guys in class.